So I'm gonna follow Henrik in his footstep here. We'll do machine learning again. And here we're gonna talk about scarce data because usually we don't have that much data. So we're gonna do some data augmentation to increase our number of data points then. So testing is expensive and time consuming, of course, and it's a limiting factor. So typically we have like 10 to 20 tests in a test campaign, for instance, and we can define that as scarce. And usually when we do machine learning models, we require a lot more data points, of course, to generate a really good fitting. It doesn't work. Okay. So we need more data points than just 10 to 20 points. So for this, we need to do some kind of strategy to make up a smart training strategy. So we're going to start here, and we used a Romberg-Osgood model with amplitude format here. And based on Young's models K and N, we can then plot or predict our stress at 1% strain here, for instance. And we adopted a machine learning model based on artificial neural network with input as E, K, and N. And then the output or the target then is the stress here at 1%. To do this, we have some underlying database, material database here. We have 96 different steels, which we took from literature then. And from each of these steels, we have, for one of the materials, we have E, K, and N. And then, of course, we can use a Romberg-Osgood model to predict our stress at 1%. Each of these materials are represented by a number of tests, of course, to generate or to extrapolate your parameters. So around 3 to 5 number of materials, tests per material. So how do we do this? I mean, if we go back to what to do in image processing, so typically you start with your original image and then you do a lot of shiftings, rotation, you shift your colors, you do croppings, you do rotation stuff, and you generate a number of artificial images of this original image. You get more data points. Well, we cannot do this for numerical models. I mean, we can't shift too much. We need to incorporate the physics. Well, we need to have the physics still. So in this work, we took 3 concepts, or 2 concepts, and a baseline. So we're going to look on, first we're going to do a baseline, and then we do a linear augmentation, and then a scatter augmentation approach. For each of these 3, we will use an artificial neural network, which is constant, and we're going to keep the hyperparameters constant. So we're not shifting the network, we're keeping it constant with 3 inputs and 1 output, and we have 5 neurons in the hidden layers. Kind of simple model. And we're using 80% of the training data and 10-20 for test. We don't have a validation test set because we want to have it constant, because we're going to run all of the simulations through 10,000 epochs. Stochastic gradient descent and a sigmoid, and the learning rates and momentum rate are also constant. We start with the baseline, and the baseline is that we have no augmentation. So we're going to use all our 96 materials and perform the training with that. So here we have all the 96 Romberg-Osgood's plots. And when we run here, we see the training here, the mean relative error then over the epochs, up to 10,000 epochs. And you still see that it's ongoing. I mean, we could continue to train this more, get a lower error, but we keep it at 10,000 epochs. And from here, we have the training and the test. And you see the test is going down to roughly 3.4% error, which is pretty good for standard fittings. And following the straight line here, the Pearson correlation coefficient. So we have that. This is our baseline. So we want to, when we do our scatter or augmentation, that we want to be below this value. Otherwise, it can be considered bad, of course. So the first thing for the linear augmentation concept is that first we need to have our scarce data. So we're going to do a uniform Latin hypercube sampling out of all these 96 tests. And we're going to choose 10 points, which is our scarce data. So we're going to rely all our augmentation just out of 10 points. And they are to be contained within this 96 then. And then we just do a linear scaling, plus minus 10%, on each of these different points then. So going from 1.1 to 0.9 here. And then you scale each of your material parameters, E, K, and N, with this linear scaling. And we have 10 times 100, we generate thousands artificial data materials then. So for each of these, we have 100, a scatter band of 100 materials, just small deviations from one of the sampling points here, for that one, for that, and so on. So from our 96, or from our 10 points, we now have 1,010, because we're going to use these inputs also. So 1,000 artificial and these 10s. So it's 1,010 training points. And when we train here, we see the mean relative error goes towards a really low value under these 10,000s. And we are on the test ones at 0.24%, which is really low percentage value in the errors. And the Pearson coefficient is more or less 1. So we generate a really good response then. If we take the next or another type of augmentation method, is called the scatter augmentation method, and this is more physically based. So we're going to use the same kind of, or exactly the same points in the Latin hypercube sampling as before. So we just have the same points here. Those are there for the the Young's modulus then. So E, K, and N. So we're going to do a normal distribution plot over these sampling points for Young's modulus here. We get that curve. And then we're going to define our 95% confidence interval. And within this confidence interval, we then do a normal, or generate normally distributed or random normal distributed points. And this randomness is constant for all of this. And within this small window, we sample, so each of these points, we then take away the mean and divide with the mean, so we get a factor, which we then again can multiply with each of our parameters. And again, we do 100 samplings, so we get 1,000 artificial materials again. And you see here, this is a little bit more widespread than the linear one, basically more evenly distributed ones. And then we train, and epochs goes towards a really good value. Not as good as the linear one. The linear one was 24. Now this is 0.26%, even though it's very good. So a summary here. If you look on our summary, the baseline is 3.3%. 0.24 and 0.26%. If you then just look on the factor normalized with the linear one, doesn't deviate that much for these two. But here you have 14%, so you beat the baseline with a really huge factor. Then again, looking on your stress range, your maximum and the minimum ones on your problem here, it's increasing with the different augmentation techniques, but not that much. I mean, we're okay, it's 100 more or less megapascals here, but one can think about how much you want to take into account. I mean, here you have a factor plus minus 10%, and here you have the sampling of the 95% confidence interval. I mean, you can change those one, and you can minimize these values also. Another thing is to think about the augmentation technique. I mean, your linear one is artificially based. This is some kind of linear function. And the scatter one is more physically based. It has a physical concept. It's based on physics. And looking on your stress values, it's more stochastically distributed compared to the scatter one because it's more evenly distributed in stress space. And complexity level, I mean, the linear one is just a linear function, and the scatter one is not that complex, but a little bit more complex than the other one. But based on this, we can say that this kind of strategy is working very good for these tasks. And of course, we can generate or use it for some other models also, which are more complex. It's just that the neural network will be more complex then, of course. So thank you very much.